Hello, this is part C of the Chapter 6 lesson. In this part we're going to finish our discussion on confidence interval estimates, and specifically we're going to talk about using confidence intervals to compare the extent of disease in two different populations. So in this section we're going to use some ideas from Chapter 3 where we compared the extent of disease in different populations. And so when comparing populations, we have kind of two generic types, exposed and unexposed. The unexposed are those people who are exposed to some risk factor for the disease, and the unexposed are not. And we had lots of different ways of measuring the extent of disease. One of those was called the point prevalence. And we had the point prevalence of the exposed and the point prevalence of the unexposed. And to calculate those, we took the number of exposed with the disease divided by the total number of exposed, or the number of unexposed with the disease divided by the total number of unexposed. And so that's all there was to calculating prevalence. These we also called proportions, or we often reported these as percentages. Okay. And so one way of comparing the extent of disease in different populations was what we called this risk difference, abbreviated RD, where we took the prevalence in the exposed population minus the prevalence in the unexposed population. Another way that we had for comparing disease was with this odds ratio, where we calculated these prevalences and then divided things, and we got an odds ratio. Now, one important thing to remember about these is that if we have a risk difference of 0, then that means there isn't any difference between these two prevalences. So that means that there's no difference in between these two populations. Likewise, if we have an odds ratio of 1, that means that this numerator is the same as this denominator, and so that means that there's really no difference in between these two populations of exposed and unexposed. So if we get a risk difference of 0 or close to 0, or an odds ratio of 1 or close to 1, that means that there's no difference between the two populations. And so to illustrate our first type of confidence interval that we're going to talk about here in this part, let's make an observation. Smokers typically have a higher prevalence of cardiovascular disease than non-smokers. So one question we might ask is, well, just how much higher is it? Is it just a few percentage points higher? Is it many percentage points higher? That's a reasonable question to ask. So to begin to answer this question, we're going to define two parameters. Let's let P1 equal the proportion of all smokers who have cardiovascular disease, and P2 the proportion of all non-smokers who have cardiovascular disease. So P1, this is just the point prevalence of our exposed population, and P2 is the point prevalence of our unexposed population. So we want to know the value of P1 minus P2. This number is what we call the risk difference. It's the difference in these the point prevalences of these two populations. Okay. Well, let's make an observation here. P1, the point prevalence of the population of all smokers, is equal to the total number of smokers who have cardiovascular disease divided by the total number of smokers. So in order to find the exact value of P1, I'd have to go out and survey every single smoker, determine if they have cardiovascular disease or not, take the number that do, divide it by the total number of smokers, and that's how I'd find the exact value of P1. Well, that's impossible to know exactly. Likewise, it's going to be impossible to know the exact value of P2. So we're never going to know the exact value of P1 minus P2. So instead we're going to have to try to estimate that difference using sample statistics. So suppose we go out and we survey 744 smokers and find that 81 of them had a history of cardiovascular disease. Likewise, suppose we survey 3,055 non-smokers and find that 298 of them have a history of cardiovascular disease. So based off of this information, we can calculate sample proportions. So we calculate P1 hat, take 81 of our smokers who develop cardiovascular disease, divide it by the total number of smokers in our sample, and that gives us 0.1089. So this number says that about 10.89% of smokers in our sample develop cardiovascular disease. That number is a point estimate of P1. Likewise, P hat 2 is the number of non-smokers who have cardiovascular disease divided by the total number of non-smokers in our sample, and that's 0.0975. So that means about 9.75% of smokers in our sample develop cardiovascular disease. That number is a point estimate of P2. So then based off of this, we can calculate a point estimate of P1 minus P2 by just calculating or subtracting P hat 1 minus P hat 2, and that gives us 0.0144. So that is, again, a point estimate of P1 minus P2. That tells us that P1 minus P2 is about 0.0114. And again, whenever we estimate something, we want to measure of its accuracy. So we're going to measure this accuracy with a margin of error, and then calculate a confidence interval estimate of P1 minus P2. And so specifically, we're going to calculate a 95% confidence interval estimate of P1 minus P2. The book talks about the details of how this is done. We're just going to use Excel to calculate this, this confidence interval. So go to the workbook chapter 6 and the worksheet risk difference. And so over here in the yellow cells, we're going to enter our sample statistics. Here's our confidence level, N1, X1. X1 is the number of successes in our first sample, N2 and X2 from our second sample. This calculates our margin of error, and then our upper and lower limits on our confidence interval estimate. So summarizing these results, we get our 95% confidence interval estimate of P1 minus P2 to be that P1 minus P2 is somewhere between negative 0.0134 and positive 0.0361. So we would interpret this in the same way as every other confidence interval. We would say we are 95% confident that P1 minus P2 is somewhere between this negative number and this positive number. Now, what's significant about that is that 0 is between these two numbers, so that means that this difference could be 0, or it could be very close to 0. Well, a difference of 0 would indicate that there's not much difference in between our two populations. So the fact that this interval contains 0 leads us to the conclusion that there is not a statistically significant difference in prevalent cardiovascular disease between smokers and non-smokers. So the fact that this contains 0, that this interval contains 0 right here, means that there's not much different in between our two populations, our exposed and our unexposed. That's maybe a little bit surprising. We would think that there's a bigger difference between these two populations, but our data indicates that there's not much difference at all. Now let's make a note here that this is a confidence interval estimate for a difference of two population proportions. So this formula for the margin of error and the confidence interval can be used in any problem asking for the difference of population proportions. The problem doesn't have to specifically ask for a risk difference, even though that's kind of what we're talking about here, a risk difference. A risk difference is just the name of a difference of two population proportions. So any homework problem that asks for a difference of population proportions, we can use this type of confidence interval that we just talked about. All right, in our next example, we're going to look at our last type of confidence interval. Suppose we want to know the odds ratio of prevalent cardiovascular disease in smokers compared to non-smokers. So the odds ratio, as we defined it back in Chapter 3, was this. We're going to take our prevalences from our exposed and unexposed populations and subtract and divide them, and that's how we get our odds ratio. Or another way to describe this using the parameters that we defined in the previous example is we'll take P1 divided by 1 minus P1 and then P2 divided by 1 minus P2. So in order to know the exact value of this odds ratio, we'd have to calculate the exact values of P1 and P2 and do this calculation. Well, as we just pointed out, we're not going to be able to find the exact values of P1 and P2. And so instead we're going to have to try to estimate those based off of sample data and then use that information to estimate the value of the odds ratio. So let's look at the same data that we just saw in the previous example. No numbers have changed there. And so we get point estimates of P1 and P2 in the same way. And so we can use those numbers to calculate a point estimate of the odds ratio. I'm going to take P hat 1, 1 minus P hat 1, P hat 2, 1 minus P hat 2, and we get this odds ratio 1.130. We're going to note that odds ratio with a hat above it to indicate that this number is an estimate of the true value of our population odds ratio. Okay. So that is a one number estimate of the odds ratio. Whenever we estimate something, we want to measure its accuracy, and so we're going to do that with a margin of error and a confidence interval. The calculations for this type of confidence interval are very complicated. The book talks about them, but like other examples, we're just going to focus on understanding how to do the calculations and what they all mean. So go to the workbook chapter 6, the worksheet odds ratio, and we enter our data here as our confidence level, our sample statistics, same as what we got from the previous example. Here it calculates the point estimate of the odds ratio, 1.130. Down here it does some intermediate calculations, and then over here it gives us the values of our lower and upper limits for our confidence interval estimate. Okay. So based off of this, we would interpret this by saying that a 95% confidence interval of the odds ratio is that the true population value of the odds ratio is somewhere between 0.87 and 1.47. Now, we'd interpret this in the same way as every other confidence interval. We would say that we are 95% confident that the odds ratio is somewhere between 0.87 and 1.47. Now, what's significant is that this interval contains the number 1. So that means that the odds ratio could be 1 or approximately equal to 1. Well, an odds ratio of 1 means that there's just not that much difference between our two populations. And so because of this, we would say that there is not a statistically significant difference between the odds of smokers having cardiovascular disease and non-smokers having cardiovascular disease. So there's a sign of the same conclusion as the previous example. There's just not that much difference between these two populations. Now let's do a quick summary of what we've talked about here in Chapter 6. We talked about many different types of confidence intervals. They're all calculated in different ways, but they have the same basic interpretation. What we're doing is that we want to know the value of some population parameter, or the comparison of two different population parameters. That's impossible to know because it requires us getting information from every single member of our population. So instead, we estimate the value of the parameter or the parameters with sample statistics, and that gives us point estimate of the parameter. But then we want to measure the accuracy of this estimate with a margin of error, and then based off of that margin of error, we calculate a range of possible values for the parameter with a confidence interval. So whenever you see a confidence interval in a journal article, just remember this is what we're doing. We want to know the value of some population parameter, but that's impossible. So we estimate it with sample statistics, we measure its accuracy, and then we form a confidence interval, which gives us a range of possible values for the parameter.